Thanks, Anthony. So in today's class, what we'll do is this. So we'll look at cluster analysis. So I think everybody could see my blank screen. So we look at these areas today. Cluster analysis. We'll just finish off. I will begin systematic sampling. Not in any detail, but we'll just look at it. In this course, we're not going to do a lot on systematic sampling. I'm interested in looking at more of the other detailed sampling designs like cluster, two-stage, multi-stage. All those things are important for us because when you leave the course, those are the names that or the areas that you're going to hear when you go outside to do anything. And then we'll look at two real-world examples. Of sampling in general. And these two real-world examples, we have two students who are in this class. We have Mr. Harun Chot, and I believe he is a research officer attached to the Ministry of Health. And we have Donald Coffey, who is the research manager at the National Insurance Board, the NIB. So they sent me two problems or two problems. Yeah, I should say two problems that can be solved using sampling techniques, and it's just good to get a sense of exactly what type of problems exist outside there that you could actually use sampling techniques to get a grip or an estimate of a particular population parameter. So we're going to look at those two examples today. They sent me some material and slides and things like that. And at the end of maybe the first hour of the class, what I will do is I will start going through those two problems because I think that at the end of the course, what I wanted to be able to do is to look at a real world problem, right? And the issue is that the problem does not come pre-packaged, meaning that you will not know which technique to use, right? So you won't know if it's cluster analysis, you won't know if it's stratified, you don't know anything basically. But after the problem, after you describe the problem, after the person describes the problem, then you will get a sense of the direction in which we are heading, or a general idea. And I always believe there are more than one solutions to a problem, right? So sometimes there are more than one solution. Right? Now, some solutions are better than the other, right? It may be construed as being better than the other. And in statistics, the way that we will define something as being better is if the variance of the estimator is smaller, right? So that's how we will define it as being a better solution. So I don't think that there's one unique solution, because sometimes when you hear the problem on the first go, you might think about some idea, you might have some idea, but then when you really, you dissect the problem or you break the problem apart, it becomes very problematic, and sometimes there are so many issues involved that some people, they get bogged down and they are not able to move forward at all. with and produce anything. And this is the part that we want to at least be able to have a push and go in a specific direction, so that we will be able to give whoever it is an estimate of what they are looking at. Right. So right. So we did a lot with cluster sampling, right? And these notes are taken from the textbook by it's called, let me get the exact name of the textbook. It's called Sampling Design and Analysis, right? So this is taken from Sampling Design and Analysis. This is actually the textbook that is used in the undergraduate course called design sampling and designs of experiments, or is it designs of experiments and sampling theory? So there's an undergraduate course that has a 50-50. Like half of the course is supposed to be on sampling designs or designs of experiments, and half of the course is supposed to be on sampling, right? And the book that they recommend is this book. To me, it's a little bit too advanced, maybe, but anyhow. So the notes that you see here on these slides that I will put up on my learning are actually from this book, right? So you can look at this after. So what I tried to do, I tried to, you know, give you proper notes on a PowerPoint, so you could have everything on one go and see exactly what we had before and what we have now. So what we had before, one of the problems, or one of the issues that always will show up is that the notations will change depending on the textbooks that you use and so on, right? And you have to be always, aware that this is more than likely to be problematic as we move forward. So we did look at a few of these points about understanding cluster sampling, what is cluster sampling, why we choose clusters, and so on. And one of the main reasons why we choose clusters is because we don't have um, any complete listing or any sampling frame of the population units. And in order to conserve time and save money, um, what we will normally do is we'll take our population and we'll divide it into what we call clusters. And these clusters are there. There's a lot of variability within the cluster, right? So within each one of the clusters, you have a lot of variability, but between clusters, you have little variability. So what you are saying is that the clusters are more or less the same, right? And the example that I used the last day, we could have, say, farmers in a particular part of the country. So you could have farmers in a particular part of the country, but you'll have like large farms, you'll have small farms, you'll have medium-sized farms, right? Like that. And also, um, in another part of the country, maybe a different county, you'll also have some large farms, right? You'll have some medium-sized farms and some small farmers, right? So this is the idea. So the idea is that within the clusters you have a high variability, but between clusters you have low variability. One of the things that one of the notion that always comes out most of the times is it's always easy to look at the case of equal clusters. Now, the reason why that is so is because we don't have to worry about the size of the clusters. But this is very hard to do in practice, right? So in practice, when we come across a real life problem, it's really difficult to say whether um, a particular after you divide the population, you'll have an equal number of sampling units in each cluster. That is very, very difficult to say, right, before you start any sampling process. So sometimes, most of the times, I should say, these cluster sizes, they are not the same, right? So they vary. And what we need to do is we need to be able to estimate these parameters. And after we estimate the parameters, yes, we would want to, look at whether cluster sampling is as good as, say, simple random sampling, or is it worse than simple random sampling, and so on. The last part that we have to look at is something called the intra-cluster correlation, the ICC. This is not the cricket board, but the intra-cluster correlation coefficient, so the ICC. And one part of the note that we did not cover so far is the estimation of proportions when it comes to cluster analysis, right? So this is a part that we did not look at, so we'll have to look at that. So all these here, I have more or less gone through, so I'm going to just skip these. I'm going to jump down to this. So when we have clusters of equal size, what we would like to do always is just to find the variance of the cluster mean. So this is y bar with a subscript CL. So this is the cluster, let's call it cluster sample mean, right? We will want to know, whether this cluster sample mean has, is it as good as the simple random sampling method, or is it, is it worse than just choosing a simple random sampling? So the variance of the cluster mean is given by this, right? So of course, we're using simple random sampling without replacement. So you have n minus n SB squared, where SB squared is given by this value here. And how do we estimate the variance? Well, you only have to estimate the parameter here, the population parameter, which is this SB squared. So this is capital SB squared, right? So what you would want to do is you would want to estimate this with the sample, with the corresponding sample version of that population parameter, which is small SB squared, which is nothing more than a sample estimate of the entire thing, right? So we have this. So this is what you use in order to construct confidence intervals and so forth. So if you want to construct, say, a confidence interval for the cluster mean, what you will do is you will normally do like, take this, right? So you'll normally have it like this. If n is large, and most of the times n is large, this value here could be replaced by z alpha on 2 or 1.96. And in fact, most textbooks I've looked at, they actually, they actually just ignore this and they just use the z value. once it's large. So how do we compare it with the simple random sample without replacement? So the first thing is this: we have to, the simple random sample without replacement, the variance is given by this, right? So remember that the total is equal to nm. You have n clusters, and each cluster has m elements, right? So the total number of values in the population is nm. So that's how you get that, right? And out of the capital N clusters, so maybe I should do a blank page. So initially what takes place is that you divide your population into capital N clusters. So you divide population into N clusters, capital N, and each cluster has capital M units inside there, right? And then what you do is you take a sample of small n clusters. So what we are going to do is we're going to take small n clusters out of those capital N. So you're going to take 1, 2, dot, 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 up to small n, right? So these here are your clusters that were sampled, right? So we'll have this situation. Now, what happens is that each cluster has m units. So if initially I had n clusters in the population and each has m units, then the total number of elements in the population is n multiplied by capital M, right? So the total number of elements in the population is nm, and the total number of elements in the sample is what? Now I have n small n clusters, right? But each of these small n clusters has what? Capital M elements inside them, right? So then it'll be n times m, right? So that's why if you want to get something like the when you're doing simple random sampling without replacement, what you'll normally put down is like n minus small n over this, right? And then you'll put like s squared, right? So this is what we normally put down when we use SRS without replacement for a single population, right? But now instead of just n here, the total is capital N M. The sample size is no longer small n, but is that, and this here is N M, and this here is N M. Right, so now things sorry, just take out this minus sign here. This is n multiplied by n, right? So now everything is in terms of capital N, everything is in terms of capital N, capital M, and small n, right? These numbers in front. So that's why you're going to see them. You're going to see this part in front, right? Okay. So when you work this thing out, you arrive at this step here, and if we want to find out whether this is in fact, is it better than simple random sampling without replacement and so on, what we'll have to do is we'll have to look at the variance of Y bar CL and see how we could break it up into little pieces. Now, when I say break it up into little pieces, this is nothing more than what you would have done. Maybe I'm just using this term um, when you did like an ANOVA table. So I'm not saying that these things are sum of squares, but these are like mean square errors, the mean squares, right? So between and W is within. So so you have clusters, right? You have groups. So you have like sums of squares between sum of squares, but then you have sums of squares within sum of squares, right? And then when you divide by the appropriate degrees of freedom, you get estimates of these things here, of the within mean squares and the between mean squares. So nothing, I wouldn't say anything is different from what we have been doing in the past. But when there is a lot of intersection, I should say, first of all, between sampling and designs of experiments. There's a lot of intersection. And when I say intersection, I'm speaking about the way that the elements are really allowed to be chosen and the restrictions that you have. So the restrictions that you have for the sampling design dictates the type of experiments that you can do, or the ANOVA that you can produce. So I'll just explain what that means. So let's take an example here. Right, so suppose we have four types of fertilizer, right? And you want to determine which one is the best fertilizer, right? And you have one variety of rice. So you have some local variety, and you want to find out, which one of these four fertilizers are the best. Then, in order to answer that, what you could do is you could take a block of land and divide it into 16 smaller plots, right? All of equal size. So I have 16 plots of land here. What I will do is this: I randomly assign the first fertilizer to four of these plots, right? So you randomly assign it. So let's say fertilizer 1 ended up here, fertilizer 1 here, fertilizer 1 ended up here, and fertilizer 1 ended up here. Then you take a second fertilizer. Let's call that fertilizer 2. So you randomly assign the second fertilizer to 4 of the remaining, right? So you have 12 now remaining, right? Remaining plots. Let's call that F2. And let's say we get these values here. Like that. And then you'll have 8 plots remaining, right? Then you randomly assign uh, fertilizer 3 to 4 out of the remaining 8 plots. So suppose you have this, and of course you have no space to put fertilizer 4, but in those blank spaces, right? So I'll just put fertilizer 4 in that, in those blanks, those 4 blank cells. So now everything is packed. All right. Now, what I said before is that your sampling design, right, or will tell you or give you an idea of how to or what type of analysis to do in designs of experiments. It's because of this. It's how you assign stuff. We were randomly assigning the fertilizer to, to each fertilizer to 4 of these smaller plots, right, at random. And you will not see this. This part here is what we call the experimental design, right? The uh, let's let's call it a visual for the experimental design. So you get a visual and see exactly what is taking place. When you plant the rice and you apply the fertilizer at the end of the 3 months or 4 months, right? However long it takes to reap, right? That crop, then what you do is this. So what you see now is what is the data that you're accustomed seeing in textbooks. So you'll see like F1, F2, F3, F4, and you'll see the amount of rice that that was reaped right from each one of the plots. So you'll have like 50, 60, 80, 100, 120, 110, 170, 140, 50, 40, 35, 20, 17, 15, 13, say 10. So from this now, so this is what you'll see, and from this, you know that if you want to compare the means, then you know you have the one-way analysis of variance, right? So you see the way that you assign the treatments to the plots tells you it's a one-way, right? Now, suppose now you come across a situation like this now, right? So you have a piece of land, but this piece of land is kind of strange, meaning that you have this whole block here. This first block is clay. This whole block here is loam. This whole block here has a lot of sand in it, so I'm going to put sandy. And this last block here, um, let's say it's a mixture of loam and sand or whatever. So I have 4 different types of land, right? And now I still have these 4 fertilizers, right? I have fertilizer 1, fertilizer 2, fertilizer 3, and fertilizer 4. And I still have my one variety of rice. And the question is now, how do I allocate these fertilizers now to these different plots that I have here, right? Or these different um, blocks of land, I should say. Well, we could do the same thing again, meaning that we can divide each one of the larger block of land into 4 pieces, right? So no problems here. But now the way in which we allocate the fertilizer to these is not at random over the 16, but you take one fertilizer, right? Like fertilizer one, and you randomly allocate it to any one of these four um, any one of these four smaller plots of land here. So suppose F1 is here. Then you take the first fertilizer again and you randomly allocate it to any one of these four plots of loam. So that's F1 here, say F1 is over here, F1 is over here. So in other words, what we are trying to do now is we are trying to have each fertilizer, right, show up on each of the different types of soil, right? So that you'll be able to cater for, any differences that can be attributed to the soil type, right? So you'll have something like this. Right? So now what you notice is that the sampling designer is completely different, right? So it's not like you're taking four and you randomly allocate it to all. You take each fertilizer and you randomly allocate it to any of the four plots. But you take the fertilizer and you randomly allocate each fertilizer to one of plot in each one of the different types of soil, right? And for those of you who would have known, this is nothing more than a what? A randomized, complete block design, right? So it is a sampling methodology that was used before that is telling you that this thing here is a randomized complete block design. It is randomized. Why? Because each fertilizer was randomly, um, placed into one of those smaller plots, into each one of those smaller plots. It's complete because we don't have any missing pieces anywhere. It's complete, right? So I have all my cells filled up. And in some books, the notion of completeness means that we have equal numbers, right? So we have 4, 4, 4, 4, right? And it's a block design because we are um, catering or trying to or I should say control for one source of variation. So the source of variation that we are taking care of here in this example is what? Is the type of what? Is the type of soil, right? And then you'll be able to work out um, the ANOVA table, enter the data in R, get the output, and analyze the output. Right. So the type of sampling that you do, right, affects the type of design that you will end up with. And that now tells you, once you have the design, you know how to analyze it. So everything is like step, 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 step one, step two, step three, right? Once you know the steps involved in the experiment, it's very easy. If you don't know or what was done, that is still a problem that uh, we try to fix after, which is not a good way of doing things, right? Right. So I have this example here. This is actually from the textbook as well. So you could just look at this example. It's just to estimate the mean and variance using one-stage cluster sampling, and an estimate of the mean and variance using two-stage cluster sampling. right? So you could take a look at this one here and see exactly how um, the calculations. Maybe I could put the calculations on my learning so you could actually see. Now, this is the part that I want to introduce to you today. This part here called the intra-class cluster coefficient. Because sometimes a lot of people ask, um, when should we use cluster sampling? Does it make sense to use cluster sampling, or should I just do a simple random sample, right? So uh, what do you really do in order to, get a good sense of whether you should do cluster sampling or whether you should just, just take a simple random sample, right? So there is this intra-class correlation coefficient, the ICC that we mentioned previously. And this tells us about the similarity of the elements within the same cluster, right? So the similarity of the elements within the same cluster. So that means that if you have a cluster like this, it tells us the similarity of the elements within this cluster, right? And the ICC is defined to be Pearson's correlation coefficient. So it's just since it's just a Pearson's correlation coefficient for n minus nm multiplied by m minus 1 pairs, right? For I between 1 and n and j not equal to k, and can be written in terms of the population ANOVA quantities such as rho is equal to this, because SSW over SST is between 0 and 1. All right, let's just step back a little bit and see what is taking place across here, right? So before you do cluster sampling, sometimes if you have information on the clusters, so if you have the values that you extracted, then you could do an ANOVA table. And what the ANOVA table does, it produces rho. And what rho tells you, rho gives you an idea if you should either stick with cluster sampling, or if you should stick with if you should stick with simple random sampling, right? So that's the main point here, right? So when the ICC is greater than 0, so when it's positive, the elements within a primary sampling unit, PSU, and maybe you might be wondering, what is a PSU? And well, a PSU is simply this. When you take your population and you divide it into clusters, those n clusters, those are your PSUs, your primary sampling units, right? That's your PSUs. So it tells us that the elements within a primary sampling unit, PSU, tend to be similar. Then SSW will be small relative to SST, and the ICC will be relatively large. When the ICC is positive, cluster sampling is less efficient than simple random sampling, right? So this here gives us an idea of the relative efficiency of cluster sampling. So in one go, we could actually say whether it is more efficient or less efficient just by doing what? Doing an ANOVA table. Now, let's just drop down now and actually do one and see how it's done. Now, the intraclass cluster coefficient, the ICC, it is only valid when for clusters of equal size. So this is the only time when you could use the ICC. So, but there will be many instances when this does not hold true, right? So there will be instances when the clusters will have different sizes, and that takes place most of the time when you do sampling. The clusters will not have the same size. It's a given, almost a given. So in that case, when the ICC fails, then you have an alternative measure called R squared adjusted. I don't know how many of you would have met R squared adjusted before, but I'll just explain what it is, right? It's easier to explain it in the context of a multiple linear regression. So say y is equal to beta 0 plus beta 1 x1. So we're looking at R squared adjusted, right? Most books don't use R squared A, they use R squared ADJ. So the ADJ means adjusted. So we are just forming, this linear regression here, right? And we want to find out, how many variables sometimes should we have, in a multiple linear regression. Because if you collect variables, sometimes it's a lot. And one of the things is, you you want to have some way where you could justify having a certain number, but you don't want, too many inside it, because if you have too many, the model becomes too long. It becomes, and sometimes it's difficult to interpret, right, with too many variables. So what we aim for in statistics is we like what we call parsimonious models. So parsimonious means it's small, but it is effective. The model is not an exorbitant model. Is not too big, but it's effective. It could get the job done, meaning in terms of prediction. Um, let's look at an example. Let's look at quartz, right? So in Trinidad, we have a chain of stores, a large chain, and let's call that chain A. Chain A, the stores name store A. And store A has a lot of, they have stores in different locations. So we have stores in, say, St. James. We have stores in Chaguanas, in San Fernando. We have a lot of stores in Curep, etc., right? So this is the location. So these are my stores, one chain. And what you are looking at, Y, is your dependent variable, and you're looking at the amount of sales that they get in 1 year, right? Or from each one of these stores here, right? So the sales. So St. James might bring in 2 million. Chaguanas might bring in 1.5 million. San Fernando might bring in 6 million, etc., right? And then you could think about, as a market researcher, you might say, what are the factors that actually contribute to my sales in each of these stores, right? So what are the main indicators that, a store will do well, in other words? So somebody could come up and say, X1 could be parking space, right? So I'll just write this. So one variable would be parking space, because if you are going to buy something and you have a car and you don't have any parking space, then and it's very difficult to get, a space, then you might not go. So your parking space that is available, say in meters squared. X2 might be the variable, might be the percentage of the store's budget that is used, say, in ads, in advertising, right? X3 might be the location of the store, right? So some stores are smack in the middle of a city center. There is no parking or limited parking and things like that. All those things, could affect it. Another variable might be the say the average income of the constituents around that store, right? X5 could be the number of employees that you have in the store, because if you have a large number of employees, then the waiting time, hopefully, will for each customer would be reduced, right? So the customer would not have to spend a long time in the store. So the number of employees, etc. So you could think up about, as you sit down, you could think about maybe about 20 different variables, right? But, but the question is this, do you really want to build one regression equation with beta x1 all the way to beta 20 x20, right? So this is questionable. This is too long. So what we try to do is we try to reduce the number of variables, right? The, the thing about multiple linear regression is this. It works like this, right? As long as the number of variables increases, number of independent variable increases, then your R squared value will increase. And your R squared value, now notice I'm not saying R squared adjusted, I'm saying R squared. And R squared just gives you the percentage of the variation in the dependent variable y that is explained by the independent variables. Now this thing is a little bit deceptive, I'll tell you why. Every time you add a new independent variable, R squared increases. So if you think about it, that's a good thing, right? So I'll just give you, if you just had one variable like this, then the R squared would be like 60%, see. And if you add another variable, whether it makes sense or not, right? So keep in mind what I'm saying, whether it makes sense or not, whether that other variable is makes sense or not, then R squared goes up to like 70%. So you keep on adding here, right? What happens is that R squared always improves, always goes up, which is good. But then the question is, how many variables do you, would you take, right? And this is where this R squared adjusted came into play. So the R squared adjusted, which we are calling R squared A in in this in this section, is simply takes into consideration the number of independent variables when uh, constructing or finding R squared. So that means R squared adjusted is going to look at the number of independent variables you have and sort of uh, don't let those variables, go out of control, meaning so that you will only have or you will only be able to take a small number or a smaller subset of those values. And this is what you want. Anytime you are doing a multiple linear regression, the what you look at is R squared adjusted, and and this is computed using information from the number of variables. So this kind of reduces or or brings R squared under control. So the increase in R squared adjusted is not as sharp as R squared. So it keeps the number of variables intact, right? Or it controls R squared for the number of variables that you have in the model. Right, so I have two examples across here that I have. So these are also taken from the textbook. And I have two populations, two artificial populations, by the way, population A and population B. Now, if you look at population A and B, so I'm just going to, put a line like this, so you'll see that this is population A, this one is B, right? If you look at population A and B, they have the same values. That's the first thing. It's the same values, but it's just arranged in a different way, right? So that means that if you just take, the ordinary y bar and your ordinary capital S squared, you'll be able to work out those two numbers would be the same for both populations, right? Because I have the same values, right? Okay. Now what we do now is that this is population A. Now this is PSU1, primary sampling unit 1. So think about PSU as cluster 1. That's all. Cluster 1, cluster 2, cluster 3. Right? So cluster 1, cluster 2, and cluster 3. Right? And I have these two populations A and B. What I'm working out now is this. I'm working out the means for each cluster, right? So if I take these three values here inside cluster 1, right? These three values here, and I work out the mean here, the mean of 10 plus 20 plus 30, and I divide that by 3, I get 20, right? So I get 20. Then I take the means of these three values now, and that's the mean of cluster 2, that's 21. Then the other mean is 19. And I work out the SI squared sample variance, the population variance, sorry, right? Because these are population values, right? So it's 100, 111, 124. And likewise, we work out these across here and the means for population B. Now, what you notice across here is that what you notice across here is this, that the values of the sample variances within the variances, sorry, not sample, the population variances within each of the clusters, they are pretty high, right? In these three clusters is pretty high. Population 1 as compared to the values in for those three clusters in population B, right? So this is very high and this is very low uh, when you compare them. So in this case here, you see most of the variability in population B occurs between clusters. So between clusters, you'll have variability, most of the variability, and you have little variability within, right? On population A, you'll have a lot of variability within, but minimal variability between, right? Right. So where does this, this ANOVA table, and where does that come from? Well, all I do now in order to illustrate, what is taking place is I construct an ANOVA table. The ANOVA table is helpful to produce the sums of squares and the mean squares. So that's all I'm doing. So I'm taking population A by itself, right? And then I'm going to take population B by itself, and I'm going to do an ANOVA table. And I'm going to treat this as treatment 1, treatment 2, and treatment 3, right? So I'll explain what I mean. So these are my values from the first population, for population A, right? And these are my 3, 10, 20, and 30. So the first three values, 10, 20, and 30, came from cluster 1. All right, so that's why, so it's going to look like this. So the data is going to be like this. So you're going to see 3 ones, right? And then you'll see the Y values will be 10, 20, 30. Then you'll see 3 twos, right? 3 twos, and then you'll see these values here, 11, 11, 20, and 32. Then you see 3 threes, right? And you'll see 9, 17, and 31, right? So you declare, so this is how you do it in R. What this is going to do, this is going to create a column with 3 ones, followed by 3 twos, followed by 3 threes, right? So repeat 1 3 times means it'll repeat that, then it'll repeat 2 3 times, then it'll going to repeat 3 times, right? So, and then I'm going to stick all that into one column, and I'm going to call that factor 1, right? And then what I do is I put the data, there's the data, my dependent variable, and I use AOV to produce the ANOVA table. And this part, the factor variable, has to be declared as a factor, right? So that's why you see as dot factor here. And then you simply do summary ANOVA dot pop e, right? So that will give you, if you look at the output in the textbook and the output here, it's the same, right? So no differences. The only thing is that in the output it doesn't give you totals, right? But of course you could add them and get your totals, right, across here for your degrees of freedom and your sum of squares. From here now, what we could do is we could actually work out things such as the R squared adjusted and rho, right? So we'll have no problem in working out these things from here. So it's 111.67. So that is the error really sum of squares minus the 84.5, and 84.5 is when you take the total. So if you take 676.8 and you divide it by 8, you're going to get this. Normally we don't do that, but in this case, to work out the R squared adjusted, this is what we do. And 1 minus that will give us this value here. So this is my R squared adjusted, and my rho value is also negative, right? I repeated the code for population B, and I got two large positive values. So population B was large and positive, right? And population A was negative, right? So what is the interpretation? The interpretation is this, that population A has much variation among the elements within the PSUs, but little variation among the PSU means. This is reflected in the large negative values of the ICC. So what does it really mean in terms of which one is more efficient than the other? Is simple random sampling without replacement, right, more efficient than cluster sampling? That's the end result. And yes, in this case, cluster sampling is more efficient. So cluster sampling is more efficient anytime because population A had what? A lot of variation within the clusters. So when you have a lot of variation within the clusters, remember the SI squares were very large. What it means, it tells you that, you know what, you should go with cluster sampling. And you could work out the ICC values and the R squared adjusted values to actually confirm that. When we look at population B, in population B, we had elements with very small variation within the three clusters. So now they were very low. So the S squared value for each one of these, S squared for each one of these were very low. And because they are very low, what happens is that this tells us that, you know what, the simple random sampling here would be the better option to go with, right? So anytime you have a sampling problem, right, one of the best things to do is just do some basic descriptive statistics first, right, between the clusters of two populations, if you are comparing more than two or one, and just by looking at this here, you could see if these things are large compared to this one, you know that cluster sampling will work well for population A, but cluster sampling will not work well for population B, right? So you want a lot of variation within the clusters. Okay, so I'm looking at the time. It's 5:12. So I said I was thought I could do more, but we'll stop here in terms of the slides. But I want to look at two problems that, you know, two students brought from their work, right? So I don't know if Donald is on. Donald, if you could just unmute, I could always move the slides up and down, so you could speak and I could move the slides up and down.
Okay, good afternoon, everyone. All right, so while preparing for coursework one, reviewing the material on ratio estimation, it occurred to me that we could probably try and use this method to solve a long-lasting problem at the NIB. So um, probably go to the other slide. Dr. Diaz. Right, so this is the issue here. So at the NIB, as you all know, the National Insurance Board is the agency responsible for the collection of contribution income and the payment of social insurance benefits for the entire population of Trinidad and Tobago, right? So it's a large organization. And at the NIB, in any given period, right, we know the total amount collected in contribution income and the total number of persons on whose behalf those payments were made, right? Good. However, currently there is no reliable way to determine the amount of income nor the number of persons on whose behalf payments were made for specific industries, right? So the NIB could report that in the last, for example, in the last 3 months, we received X amount of contribution incomes. We have no way of saying we received X amount of contribution income from the oil and gas industry, or from manufacturing, or from this or that sector. We don't have any way of doing that currently, right? So of course this has implications for our ability to establish trends in contribution collection at the industrial level and to develop more targeted approaches for the recovery of contribution income from specific sectors. So we can't look and see how things are changing over any given period of time using any kind of time series methods to see how contribution income is evolving at the industry level. We could only see how it is evolving at the level of total contribution income, right? Okay. So that's a little synopsis of the problem. So how we could use ratio estimation probably. My basic idea, is okay, because of the large number of employers that remit contributions on a monthly or annual basis, right? So we're talking about what, 18 to 19,000 employers every month remitting contributions. And in any given year, it's over 20,000 when you look at the unique number of employers, right? So, because of course, from month to month, you would have the same employers, more or less, the majority of them remitting contributions. So it's a large number of employers. There's no way we could look at all of those employers and classify them by industries and break it down to look at what is happening at the industrial level. It's just too much work, right? So what we could do, however, what's conceivable is that we could take a sample of those employers, right? And we could probably use as a stratifying variable the size of the employer, perhaps. And this smaller number of employers could be classified by industry using an international standard. So there's actually an international standard for industrial classification, right? And with a smaller number of employers, that's much more manageable. We could classify them properly, take our time and classify them properly, and then use that information. We could um, estimate then the amount of income and the number of workers for whom income was received for each industry. So I guess in this case, the big X or big X bar, if you're looking at average contribution income, will be the total number of contribution income. And then small x bar will be the average from a particular industry, and the y will be, I guess, the total income for the sample, or the average income for the sample, something along those lines. And this is how I guess we could use this method to actually, you know, provide some kind of something for the organization to work with in terms of looking at how contribution income evolves at the industrial level and how many persons we are receiving contribution income for at the industrial level. Yeah, so that's basically it.
Yeah. So in the so all the problems sometimes that people face, right? What they can get estimates from the sampling area. So from this course, there are a lot of problems I hear people talking about, like in the news, that they are not able to do this, they are not able to do that, and the other. But the material in this course will enable a lot of people to be able to provide, I wouldn't say accurate 100% accurate estimates, but estimates that are reliable, and we could use ones that have um, small variance, right? A small variance. So what Donald was saying is that at the NIB they have roughly about 20,000 employers. So this is the first thing every year. So the approach is this that he was thinking about. You take a sample of employers, because we cannot classify all these 20,000 employers. It'll take too long, right? So take a sample of employers. So maybe you take, say, n is equal to, say, 200 employers, small n. This is your big N. What you want to estimate now, what will happen is this, that you're thinking of, he's thinking about doing ratio estimation. So he's interested in the actual variable y is, I guess, is the contribution or the income that's coming in, and x has, so this is your study variable, and x is what is called your auxiliary variable. And this auxiliary variable, by the way, x is the size of the company, right? Or the size of the employer, the number of employees in the company. So what this means is that as the number of employees increase, let's call that x, the total contributions paid by that employer will increase. So if you plot it, you should get some sort of linear relationship. So you know that, okay, ratio estimation appears to be, a good approach here. But he's not out of the woods as yet, right? Because now uh, what he's doing is he's taking this n is equal to 200 employers and classifying them. So you have maybe 200 employers. So 1, 2, 3, 4, like this. So these are your employers. So these are your Y's and these are your X's. So this is the X's is the number of employees, say, and Y is the total contribution by a particular employer. And on the end across here, you could actually have the classification. If the employer is a SME or small and or large industry, or which one of the international classifications does the employer belong. Now, the approach that he's using is y bar hat, the ratio estimator, would be the mean of all the contributions over, we could use the average number of employees over the total average, right? So you could actually use this and you could estimate y hat ratio, which is y hat ratio is just an estimator of y bar. And if you estimate y bar, then you just multiply 20,000, because that's how much employees you have. If you multiply 20,000 by y bar, that you should be able to estimate the total the total contributions for the year. So there are ways in which you could do these things. Another way is when you choose these 200, you could break them up into different classification one time. So you go through all and you say, okay, we have 50 that belongs to classification 1. You have 40 that belongs to classification 2. And then you do the ratio estimation within each of these groups here. So now you'll be able to get means now for each one of those groups, right? And so you'll have a good idea of how the contribution or the relative contribution each industry has in terms of that they pay to the NIB for the employees for the entire year. Right. That's a I don't know if Donald have anything else to add. We have a second one. Second. Right. So this one is given by Harun Chot from the Ministry of Health, and this is a very timely problem that is taking place right now, especially with COVID-19. So Harun, I don't know if your mic is working. If it's not working, you could just type on the chat, and I'll just go through it.
Good afternoon.
Oh,
You're
right.
hearing me?
Yes, it's perfect. Right. Go ahead.
So I work in the Ministry of Health, specifically the Directorate of Women's Health. So we develop policy and clinical guidelines, etc., specific to women's health. We've our director, Dr. Surjit Singh, he's been on TV a couple of times. You might have seen him. He made sure to collect data for all pregnant women who presented to public as well as private health facilities who had flu-like symptoms and were in contact with a COVID-19 positive patient. And the reason why that is important is because those were the people who would have to be tested. So all patients who presented to the maternity units in the country or to the private maternity units, if they showed symptoms, they would have been tested. And of course, as we know, some of them returned positive, were positive for COVID-19. The questioner was asked just 2 days ago. Was this question number one, which is on your screen? Do we have a greater prevalence of COVID-19 positive women in Trinidad and Tobago as compared to the rest of the world or as compared to the PAHO region? And it makes you wonder other questions, which is like question 2 and 3. How many pregnant women contracted COVID-19 in the PAHO region, PAHO being all of the Americas, so North America, South America, Central America, as well as the Caribbean, and how many women have contracted COVID-19 in the world? Now, some of you may assume that this is readily available from the WHO, etc. But remember, we don't even know how many people contracted COVID-19 at all, because some countries didn't start collecting the data until they had their first wave or their second wave, etc. And of those countries or of those places that collected data on COVID-19 patients, many times there was the immediate problem was COVID-19. They weren't really checking to see which ones were pregnant women, which one, they just collected male, female kind of thing. So there were some studies that were published in countries that had observatories, observatories that similar to like what we have in Trinidad and Tobago, where they collect data specific to maternal data, let's call it that. So you would see the first one, the CDC, and again during that time period, January 22, October 3rd, I believe that would be 2020. That was when the US had a large number of cases, they collected this data specific to pregnant women. So we have a specific data, a specific time in of data being collected in a specific jurisdiction. Similarly, in the UK, what I just copied and pasted here was from some of the published studies. The UK also has an obstetric surveillance system, and again, for a specific time, 1st of March to 14th April 2020. So again, that's only a month and a half. They got permission to collect this data and to publish this data with regard to some of these women who had contracted COVID-19. And then similarly, a similar situation in the Netherlands, where they collected data between March 1st and 31st of August 2020, and it shows the number of pregnant women who were registered who were COVID-19 positive. And then we have an estimate from PAHU. Well, when I say it's an estimate, it's confirmed cases, but remember, not everybody is tested. Even pregnant women, not all of them were tested for COVID-19. So if they came in asymptomatic without any symptoms, most likely a COVID test wasn't done on them, even though they may have been COVID-19 positive. So after all of that, how do you answer the question that was initially shown? How do you find out how, if Trinidad and Tobago has a higher or lower prevalence for COVID-19 positive pregnant women compared to anywhere else, whether it be PAHO region or whether it be the world in general? So I was wondering, I just sent an email to Dr. Dial saying, I was just wondering, is it possible that we'll use each country as a cluster? I don't know how to deal with the different time periods because, of course, the wave-like features of the epidemiological curve, where you have a first wave, a second wave, etc. And then with the introduction of vaccines is another thing. How do you estimate this? And I didn't have as much time, obviously, to think about it as Donald had with regard to his situation. So I just send this for us to discuss as a class. I don't have any, I can't give any suggestions like how Donald did.
Yeah, so this is an interesting problem. The first thing is this, that what we have is has been people who are positive, or pregnant women who are COVID positive, right? They are only the ones who are tested. Of course, there would be a lot of people who would be pregnant who would have this virus who would not be tested. So the first thing is what we report. So what has been reported is usually an underestimation of the extent of the spread. You see, this is really important. And unless you could get an idea of the of this part here, then you can't move forward. Meaning that what is really important for us, I believe here, is to find some percentage of COVID-19 pregnant women who don't show any symptoms. Who don't show any COVID-19 symptoms. Now, why is this important, right? Now, I know that, why is this here important? Because this will tell us the degree to which we have been underestimating the numbers of COVID positive pregnant ladies, right? One way you could do this, one way you could get an idea of this, is you could actually, well, you'll have to take a random sample. of women who are in the hospitals or who are going to the hospitals, and say of 100, and out of the 100 now, you'll have to maybe say 50 are tested as having COVID, but out of the 50, you see, you said that you are only testing them, right, if they show symptoms. That's a big problem.
Yeah, they only tested if they're symptomatic.
Yeah, and I guess one of the reasons for that is because it's costly to test, right? So that's the reason why they don't offer the test for everybody. So even when you're going to take the vaccine, I believe they ask you, do you have COVID? Now, if you never did a test, I don't know how you'll know if you never had COVID, right? So I guess these questions are neither here nor there. So you will need to find out, out of like 100 women, you'll have to test all. You'll have to give all 100 this COVID test. These pregnant women who are in the healthcare system, right? Now you will know now how many are truly COVID positive. So you will say, okay, you'll have like 60 uh, COVID positive, 40 no COVID, right? Now, out of this 60 now, now you will be able to ask other questions. You'll be able to say, um, you'll be able to look at the patient and actually see whether the person, ask the patient if they were um, if they came close to a person with COVID-19, or if they are, just a carrier. They appear normal, but they don't show any symptoms of this disease. So say 20 out of the 60 show no symptoms.
Excuse Dr. Dialsing. Also,
Yeah.
when you're taking this sample, you'll have to take a sample of either vaccinated or not vaccinated.
Right.
Because we
Right.
took so long to
So
collect
yeah.
the data. Yeah.
Right. So the thing is, maybe you might have to take like 200, and out of the 200 you'll have vax and not vaccinated. So now you'll have what eventually you would end up with is something like this. Now, there are many other variables I guess you could think about. So, unvaccinated, positive, negative, and maybe 60, 40, maybe 50, 50. Maybe you end up with this, right? Out of the positive, well now we know that even though you're vaccinated, you could be a carrier. So now that's out of the 60 now who are vaccinated, who are positive now, you will look at their symptoms and look at them and have a doctor look at them, and the doctor will be able to decide, if this person is just a carrier or if this person has all the other symptoms attached with COVID-19. So the doctor might come away saying that, 20 out of 60 that were vaccinated show no symptoms or were asymptomatic, and maybe 10 out of 50 were asymptomatic as well. So no symptoms here, no symptoms across here. Now, these are the numbers you're going to use now to inflate the values. So this is 1/3, and this is what? This is 1/5. Now you see, depending on what information you have so far, that is all that you would be able to get, right? So if a person comes in who is so when you take when you are estimating your total in terms of the total prevalence. You'll have an idea of the prevalence of the disease among the unvaccinated and the vaccinated. But not only that, you'll have an idea of the percentage of those who are vaccinated who are carriers who don't show this any symptoms, and you'll also have the percentage of the non-vaccinated who don't show any symptoms. Now, these two things are very important. These two percentages are very important because what that will do is that will tell us or give us an idea of by how much we should inflate the numbers by. So if you know a certain percentage of the healthcare system, well, you will not be able to know everybody's, but suppose you have maybe say 3,000 people in a year, right? And you'll know exactly when vaccination started. Then you could use the numbers up here for non-vac to give you an idea of the estimate of the people who have COVID-19 and maybe half of the year. So again, the time period when vaccination started would be a little problematic, right? And who got vaccine and things like that. So even before you even think about vaccine and non-vaccine, it might be even better just to just get an estimate and inflate the estimate of the number of COVID-19 cases by the percentage who showed no symptoms, but yet they are positive. And this is the only way I could think about that you could actually do that. You have to take some random sample. You have to get, you have to know the patients. You have to administer a COVID test to all 200. And if you want to be fancy, yeah, you could do the vaccinated and the unvaccinated. And so you could actually see whether, if it's really true, what has been shelled out there that, that once you have COVID-19, then you really would not, if you have the vaccine, you will get sick, yes, but you will not get, you might not end up in ICU and or get very sick. All these things, but I think getting this information is the first point of call. You get these percentages right, then you'll be able to inflate these numbers, because in the reason why I say you have to inflate the numbers is because you are only doing tests for those who show some symptoms, right? So you're not testing everybody. So because of that, you'll have to inflate the numbers, and you'll have to do something that estimates these percentages in a proper way. If you just go in a very ad hoc way and from what you observe, that might lead to a lot of biases, right? Some people, and it's very subjective in the way that some people may have a little cold. It may not be COVID, but once you have something, they think that you have COVID. So I think the first plan of attack is to get these percentages right. You get these percentages right, then you'll be able to even estimate the total number of people or pregnant women with COVID, and so you could estimate properly. And if you estimate properly, you will be able to determine whether if you need beds in those wards, like special beds to cater for these things, or you don't need it. Right? So the first thing is to get the percentages right, because those percentages is going to help you in inflating the numbers to the correct numbers. As is now, if you just have the observed values, those are not good enough.
Okay.
So I don't know. Yeah. So I don't know if they could do this. Once they do this, then it's, I wouldn't say it's a done deal, but you will get a good idea of what is happening and how many really have it, how many are vaccinated and really have it, and things like that. So you could end up with a lot of nice estimates for these numbers. I don't think getting the values from, like, I know you showed me some papers down here from the Netherlands and from the UK, but they actually do a lot of testing and things like that. We don't do a lot of testing, and maybe one of the reasons why we don't do it because it's expensive, right? So maybe that's why it's only when symptoms show up then you are tested for COVID rather than. So there would be some people who have antibodies within them who would have had COVID. It would have passed out as a cold, like a common cold, and now they are immune. So in a case like that, how do you treat people who have already have these natural antibodies, right? So I think the percentages is the first way to go, and then after that you could get the estimators by inflating the numbers appropriately, right?
Okay, thanks, Dr. for the answer. I'll see what
Okay.
I could possibly inveigle people in the office to try to.
Yeah. Well, I mean, you will find uses for sampling all over the place. And a few years ago, when I started the course, the Minister of Finance was actually looking at the amount of money that people use their credit cards and they buy stuff away, and they wanted to estimate. I believe they wanted to estimate the amount of money that was spent on credit cards for foreign purchases. To me, that is a simple. Um, to me, it appears very easy to do just by using a simple ratio estimator. So what you would hear in the news and things, especially you'd hear problems, being related, and from the time you hear the word estimate, or a few days ago, I was listening to the news and they said that the BIR does not collect, I think, $5 billion in revenue every year. Now, how did they come up with that number, right? So all those things, you could use sampling theory to estimate all those things and actually have it in a really rigorous way, and not just like a hearsay way where you say that we are not collecting enough from oil and gas, and we don't know how the computations really come or add up to this 5 billion. It could be more, it could be less, right? And what error is attached to this, we don't know, right? So in all these cases, especially in the news, as you listen to the news, you read the newspapers, and from the time you see estimates and estimator and things like that, the number of cases, these things, you have applications of sampling theory in all these cases, right? So we'll stop for today. I want to thank Donnell and Haroon for sharing those problems with us, because one of the goals was actually to expose you to these problems. And later on in the course, I have two other past students, the acting director of the CSO, and Andre Blanchard, and Stefan Samuel, who is one of the research managers at TATT. And they will be coming in. I've asked Stefan to take you all through from the sample size determination to the end of the survey, so you actually get a sense of the entire process. And I am asking Andre to just speak on the different surveys that they do and the problems that they encounter in getting information, because all these are problems that people face.